Global retail logistics generate millions of data points every second. Managing a supply chain at this scale requires predicting demand weeks or months in advance. Multi-horizon forecasting projects multiple possible future trajectories simultaneously to anticipate long-term demand. Generating these requires processing heterogeneous data streams: time-invariant static covariates like store locations, time-varying known inputs like scheduled promotions, and time-varying unknown inputs like sudden foot traffic fluctuations. Feeding these wildly different data types directly into a standard predictive model causes it to break down. The network struggles to weigh a static ID against a rapidly fluctuating sales figure, destroying forecast accuracy. For years, engineers relied on long short-term memory networks to handle time series data. While LSTMs process sequential steps well, they suffer from vanishing gradients when sequence lengths increase, meaning they lose track of long-range dependencies. Standard transformer models resolve the long-range issue using self-attention mechanisms. However, they struggle to effectively incorporate static context and frequently miss highly localized step-by-step sequential dynamics. The Temporal fusion transformer, developed by Google researchers, resolves this tension by synthesizing the strengths of both architectures into a single forward pass. The architecture selectively routes temporal features through recurrent LSTM layers for local processing, and then passes those outputs to a modified multi-head attention decoder to map long-range dependencies. By assigning the right structural tool to the right type of data, this hybrid design achieves high predicted accuracy, while providing mathematically explicit explanations of what drove the forecast. To see how this architecture operates, we have to track a complex dataset from its initial ingestion. This diagram represents a raw dataset being physically split into 3 distinct tensor blocks based on temporal behavior: static, known dynamic, and unknown dynamic. Rather than concatenating all these mixed inputs together into one dense, noisy vector, the temporal fusion transformer isolates them. Before entering the deep network, each stream hits the variable selection networks. Inside, nodes brighten or dim as the model evaluates feature importance per time step, suppressing variables lacking predictive power. This dynamic weighting ensures adaptation. If a trend loses relevance, the network downweights it instantly. As a result, noise from less significant features is stripped away before the data ever reaches the recurrent layers. Variable selection networks solve the core problem of heterogeneous data ingestion. They ensure that only high-signal inputs proceed deeper into the architecture. Once the data is filtered, the model faces a new challenge: controlling its own internal complexity so it doesn't overfit on the refined inputs. The primary structural safeguard here is the gated residual network. This gated residual network schematic features an internal gated linear unit, or GLU. It acts as a mathematical gate, opening and closing to control data throughput. This allows the network to adapt its depth, suppressing entire subnetworks so simple data skips unnecessary processing layers. Standard deep learning models are structurally rigid. Their static depth forces the network to memorize noise when presented with simple data, leading to severe overfitting. By utilizing gated residual networks, the model maintains the capacity to handle highly complex temporal sequences while safely gating off complexity when it isn't needed. With the data filtered and the network complexity regulated, the inputs move into the sequence processing phase. The static tensor block routes into a static covariate encoder, instantly transforming into a highly dense context vector. This vector drops down to initialize the starting hidden state of an LSTM block. Only then do the dynamic data streams enter, processing sequentially step by step. The LSTM layers extract highly localized sequential patterns, passing relevant temporal information from one step to the next. Initializing the network state with a single static context vector is far more efficient than the traditional method of awkwardly appending static data to every single time step along the sequence. This precise sequence of operations guarantees that the LSTM's localized processing is mathematically anchored by unchanging background variables, like product IDs or demographics. To connect these localized patterns across extended timelines, the data enters the final architectural phase, the temporal fusion decoder. Hidden state outputs flow from the LSTM into the temporal fusion decoder, separating into multiple attention heads. These mechanisms weigh historical time steps against each other. Connecting lines dynamically thicken to indicate higher attention weights. Evaluating the entire sequence simultaneously gives the model a global view of the data, entirely bypassing the vanishing gradient limitations of the earlier LSTM layer. But here, a unique modification occurs. The individual attention heads merge their separate value matrices into a single, unified shared block. The network then uses additive aggregation to combine these values. Sharing values prevents the network from obscuring its decision-making logic across separate mathematical subspaces. It explicitly calculates exactly which features drove the final prediction. This exact modification secures the long-range predictive accuracy of a transformer while retaining the transparent interpretability demanded by high-stakes enterprise forecasting. Transitioning this theoretical architecture into a production environment requires specific engineering considerations. The model's complex routing demands significant computational resources, and achieving the benchmarked accuracy of the original paper requires rigorous hyperparameter tuning. This matrix displays the primary PyTorch implementations available to engineers today. The PyTorch forecasting library offers tight integration with PyTorch Lightning. It uses a specialized time series dataset object to easily manage critical constraints, like max encoder length for the lookback window and max prediction length for the forecast horizon. Alternatively, the NVIDIA Deep Learning Examples repository focuses entirely on hardware optimization. It trains with mixed precision using tensor cores and natively handles the missing data commonly found in messy production environments. Selecting the appropriate implementation dictates whether a team is prioritizing rapid prototyping or production-scale hardware optimization. Regardless of the deployment environment, the final output generated by the Temporal Fusion decoder is not a simple single-point estimate. This chart illustrates the model generating probabilistic forecasts. The core projection is surrounded by widening bands, representing prediction quantiles like P10, P50, and P90. Mapping these values quantifies mathematical uncertainty, providing exact risk parameters for downstream decisions. The architecture's success comes from its refusal to force a single paradigm onto highly heterogeneous data. It orchestrates recurrent layers for sequences, attention heads for long-range dynamics, and selection networks for noise reduction. By dynamically routing data to the structures best equipped to handle it, the Temporal Fusion Transformer provides a highly accurate, fully interpretable architecture capable of resolving the most complex multi-horizon forecasting challenges in modern machine learning.